Imagine for a moment that you're floating in the deepest, darkest void of space, staring into a region where reality itself seems to break down, a place where light cannot escape, where time behaves strangely, and where the very laws of physics, as we know them, might be rewritten. This isn't science fiction. It's the enigmatic reality of black holes, cosmic phenomena that have fascinated and mystified scientists and dreamers alike for decades. What if everything we thought we knew about black holes was wrong? What if these celestial monsters are not just destructive voids but gateways to new universes, cosmic recyclers, or even keys to understanding the birth of everything we see around us? Today, we're embarking on an extraordinary journey through 25 of the most compelling and mind-bending theories about black holes, ideas that stretch the limits of our imagination and challenge our understanding of the cosmos. From the possibility that black holes could be portals to other dimensions to the startling suggestion that they might not be entirely black after all, each theory opens a door to a universe of wonder and scientific curiosity. We'll explore concepts that sound like they belong in the pages of a fantasy novel, yet are grounded in cutting-edge research and the brilliant minds of astrophysicists around the world. This is not just a list of wild ideas, it's a curated exploration of hypotheses that could very well reshape our entire view of space, time, and existence itself. As we dive into these cosmic mysteries, prepare to question what you thought was possible. We'll venture into theories about black holes birthing new universes, serving as cosmic archives, or even holding clues to the nature of dark matter and dark energy. Each concept is a piece of a grand puzzle, one that humanity has only just begun to solve. So settle in, open your mind, and join us on this voyage through the unknown, where every theory we explore might just be a step closer to unlocking the deepest secrets of the universe. Our journey begins with one of the most captivating and profound ideas in all of theoretical physics, the possibility that a black hole is not a final destination but a gateway. This theory proposes that the immense gravitational collapse that forms a black hole could actually be birthing something entirely new on the other side, a separate universe with its own physical laws and constants. It's a concept that feels ripped from the pages of the most ambitious science fiction, yet it emerges from the complex mathematics of Einstein's general relativity. The equations suggest that the extreme warping of spacetime at the heart of a black hole could become so severe that it effectively pinches off from our own universe, creating a bridge, known technically as an Einstein-Rosen bridge or a wormhole, to another cosmic realm. This idea offers a potential and elegant solution to one of the most vexing problems in modern physics, the black hole information paradox. According to quantum mechanics, information about what falls into a black hole can never truly be destroyed. But according to general relativity, anything that crosses the event horizon is lost forever to our universe, irretrievably crushed at the singularity. This creates a fundamental contradiction between our two best descriptions of reality. The gateway theory neatly resolves this. The information isn't destroyed, it simply travels into a new universe, preserved forever but utterly inaccessible to us. Our universe's lost information becomes that new universe's initial conditions, the cosmic data from which its own stars, galaxies, and perhaps even life might one day form. Of course, the practicalities of using such a gateway for travel are, to put it mildly, daunting. Any object approaching a stellar or supermassive black hole would be subjected to unimaginable tidal forces in a process physicists call spaghettification, stretched into a stream of atoms long before reaching the central point where this theoretical gateway might exist. Furthermore, most theoretical models suggest these wormhole bridges are highly unstable, collapsing faster than the speed of light, making passage impossible. Yet, the theory remains profoundly important. It challenges us to think of black holes not as cosmic dead ends but as potential catalysts for creation. forever linking the fate of our universe to the birth of countless others in an endless, unfolding multiverse. Yet if a black hole is a one-way street into oblivion, what lies on the other side of that street? This line of questioning brings us to one of the most symmetrical and elegant ideas in cosmology, the concept of white holes. If a black hole is a region of space-time from which nothing can escape, a white hole is its theoretical opposite, a region of space-time into which nothing can enter. Instead of pulling all matter and energy inward, a white hole would violently expel them, acting as a cosmic fountain of infinite energy, a source rather than a sink. The mathematics of general relativity doesn't just allow for this possibility, it practically suggests it. The same equations that describe a black hole are time-symmetric, meaning if you reverse the direction of time in the math, a black hole's event horizon suddenly becomes a white hole's, gushing out everything it once consumed. The most captivating extension of this theory proposes that a black hole and a white hole could be two ends of the same cosmic structure, connected by a tunnel through space-time known as an Einstein-Rosen bridge or a wormhole. In this model, anything that falls into the black hole in our universe could be ejected from a white hole somewhere else, perhaps in a distant part of our cosmos, or even in an entirely different universe altogether. This creates a breathtaking vision of the cosmos as a vast network of tunnels, with black holes serving as entrances and white holes as exits, ferrying matter and energy across impossible distances. It transforms black holes from grim endpoints into potential transporters, cosmic subways linking one reality to another. So why, if the math supports it, have we never observed a white hole? The prevailing hypothesis is that they are incredibly unstable. Most models suggest that the moment a white hole forms, the very act of matter trying to enter it, even a single photon of light, would cause it to collapse instantly back into a black hole. Their lifespan could be so infinitesimally short that they blink out of existence almost the instant they form, making them virtually impossible to detect with our current instruments. However, some physicists have proposed a fascinating alternative. What if the Big Bang itself was a white hole? This idea suggests that the initial singularity from which our entire universe exploded could be viewed as the ultimate white hole event, spewing out all the matter and energy that would eventually form everything we see today. This provides a beautifully cyclic view of cosmology, where every black hole collapse in one universe could be the white hole birth of another. While direct observation remains elusive, the mathematics continues to become more sophisticated. Recent quantum gravity models, particularly within loop quantum gravity, have provided new support for the white hole concept. These models avoid the problematic singularity at the heart of a black hole by suggesting that immense gravitational pressure eventually triggers a quantum bounce. In this scenario, the collapsing matter of a dying star doesn't crush into an infinitely dense point, but instead reaches a limit where it rebounds, transforming the black hole into a white hole. This process would likely happen in a tiny fraction of a second from an outside perspective, but for an object falling in, the journey through the tunnel could appear to take much longer, offering a hypothetical pathway through space-time. This theoretical persistence encourages scientists to keep searching for potential signatures, such as brief, inexplicable bursts of high-energy radiation that have no other obvious cosmic source. The hunt for white holes pushes our understanding of physics to its absolute limits, challenging us to see the universe not as a collection of separate objects, but as a deeply interconnected and dynamic whole. But if black holes can theoretically birth new universes or connect to white holes, what if they are also responsible for shaping the very fabric of our own? This leads us to a theory that reimagines the most elusive substance in the cosmos. We now turn our attention to the compelling proposal that black holes themselves could be the mysterious dark matter that has confounded astronomers for decades. For years, the prevailing hypothesis has been that dark matter is composed of some exotic, undiscovered particle, a WIMP or an action that barely interacts with normal matter. However, despite decades of searching with powerful particle colliders and sensitive underground detectors, no such particle has been found. This lack of evidence has opened the door for an audacious alternative. That dark matter isn't made of tiny particles at all, but instead consists of a vast number of ancient black holes that formed in the first fraction of a second after the Big Bang. These are not the black holes we know from stellar collapse. Primordial black holes are a different class entirely, thought to have been forged from the extreme densities and pressures present in the universe's infancy. Imagine the cosmos just moments after its birth, a seething, turbulent sea of energy. Within this chaos, random fluctuations in density could have been so intense that regions of space spontaneously collapsed under their own gravity, pinching off into tiny, incredibly dense knots of matter. These primordial black holes could range in size from smaller than a single atom to larger than a star, and they would have been scattered throughout the emerging universe like seeds. Because they formed before the first stars and galaxies, they would be invisible, nearly undetectable, and yet their collective gravitational pull could be the hidden scaffolding upon which the entire visible universe was built. The beauty of this theory is its elegant simplicity in solving multiple cosmic puzzles at once. It provides a gravitational source for dark matter without requiring any new physics beyond general relativity. These ancient black holes would naturally cluster in the halos around galaxies, their combined mass perfectly explaining the observed rotation curves of galaxies that first hinted at dark matter's existence. Their gravity would also bend the light from distant objects, creating the intricate patterns of gravitational lensing we see today. Furthermore, the theory offers a potential explanation for the existence of supermassive black holes found at the centers of galaxies. How did these monsters grow so large so quickly? If a galaxy's core was already seeded by a massive primordial black hole, it would have had an enormous head start on accumulating mass over billions of years. So how do we search for something that emits no light and could be almost anywhere? Astronomers are employing clever, indirect methods to hunt for these elusive objects. The primary tool is microlensing. When a compact, massive object like a primordial black hole passes directly between Earth and a distant star, its gravity acts as a lens, focusing the star's light and causing it to temporarily brighten. By continuously monitoring millions of stars in nearby galaxies like the Andromeda Galaxy, projects like the Subaru Telescope's Hyper-Subprime Cam survey are scanning for these characteristic, unpredictable flashes. The duration of the brightening event can even hint at the mass of the object causing it. A flash lasting a few hours might indicate a small, asteroid-mass black hole, while one lasting months could suggest a Jupiter-sized behemoth. Other search methods include looking for the telltale gravitational waves emitted when two such black holes spiral into each other and merge, precisely the type of event LIGO and Virgo have been detecting. Intriguingly, some of the black holes observed in these mergers fall into a mass range that is difficult to explain through standard stellar evolution, making them prime candidates for primordial origins. While the evidence is not yet conclusive, each new observation helps constrain the possible masses and abundances of these ancient objects. The hunt for primordial black holes as dark matter is a breathtaking example of scientific ingenuity, turning the cosmos itself into a vast detective agency where every flicker of light and ripple in space-time could be a clue to uncovering the true nature of the universe's hidden mass. However, this elegant solution to the information paradox introduces a new and profound puzzle of its own, one that strikes at the very heart of the conflict between quantum mechanics and general relativity. If a black hole evaporates completely, radiating away all of its mass and energy into the universe as a form of heat, what happens to all the information about the things that fell in? A book burned to ashes still retains its information in the arrangement of the atoms, we could, in theory, reverse the process and reconstruct the book. But Hawking radiation is purely thermal, random noise containing no discernible data about its original sources. This suggests that all the intricate information about every star, planet, or spaceship that ever crossed the event horizon is fundamentally and irrevocably lost, erased from the universe. This violates a core tenet of quantum mechanics, the principle of unitarity, which states that information must be preserved. You cannot simply delete the universe's history. This black hole information paradox has been one of the most heated debates in theoretical physics for decades, pitting the great minds of our time against each other. Stephen Hawking himself initially believed that information was truly lost, a stance that implied even our most fundamental laws of physics were incomplete. Others, like Leonard Susskind, argued fiercely that information must be preserved, leading to his development of the holographic principle. This revolutionary idea suggests that all the information describing a three-dimensional volume of space, like the interior of a black hole, might actually be encoded on its two-dimensional boundary, the event horizon. In this view, the information isn't lost inside. It's smeared across the surface like a cosmic fingerprint and is eventually released in a scrambled but recoverable form through the Hawking radiation itself. While the exact mechanism remains one of the biggest unsolved problems in physics, the consensus has gradually shifted toward information preservation, a testament to the power of a paradox to drive scientific discovery forward. The implications of Hawking radiation extend far beyond the fate of a single black hole, reaching out to dictate the ultimate destiny of the entire cosmos. In our universe's far, far future, trillions upon trillions of years from now, all the stars will have burned out and galaxies will have drifted apart into a cold, dark, and empty void. But the black holes will remain, silently orbiting in the darkness, and over almost incomprehensible timescales, they too will begin to evaporate. The largest supermassive black holes, with masses billions of times that of our Sun, would take an estimated 10 to the 100th power years to evaporate, a number so vast it dwarfs the current age of the universe. But eventually, even these titans would succumb, emitting their final burst of radiation in a quiet, unseen farewell. This paints a hauntingly bleak picture of the universe's final state, a near-perfect vacuum, sprinkled with a thin, cold gas of photons and other fundamental particles, all traces of structure and complexity long since faded away. It's a fate known as the heat death, and Hawking radiation is a key player in bringing it about. Yet, within this profound melancholy lies a spark of wonder. The idea that even the most voracious, immutable objects in creation are not eternal, that they too are subject to the subtle and strange laws of quantum mechanics, forever links the fate of the largest structures in the universe to the smallest, most fleeting fluctuations at the edge of reality. It suggests a deep and beautiful connection between the very big and the very small, a cosmic balance where even a black hole's reign must one day, however slowly, come to an end. This brings us to one of the most radical and controversial ideas to emerge from the information paradox debate, the black hole firewall. What if the event horizon is not the smooth, uneventful gateway predicted by Einstein's equations, but is instead a violent, searing wall of fire? Imagine approaching a black hole, expecting to cross its boundary without even noticing, only to be instantly incinerated by a blazing curtain of high-energy radiation. This isn't a tale of cosmic horror. It's a serious proposal put forward by physicists trying to resolve the fundamental conflict between quantum mechanics and general relativity. The firewall hypothesis suggests that to preserve the sanctity of quantum mechanics and ensure information isn't lost, the event horizon must be a special and destructive region, a literal wall of fire that completely annihilates anything attempting to pass through. The paradox that birthed this idea is a thought experiment involving two particles entangled at the edge of the event horizon. According to quantum mechanics, particles can be intimately linked or entangled, such that measuring the state of one instantly determines the state of the other, no matter the distance between them. Now, imagine one of these entangled particles falls into the black hole while its partner escapes as part of Hawking radiation. To preserve the information about what fell in, the escaping particle must become entangled with all the other Hawking radiation particles that came before it. But this creates a problem. The original particle that fell in is still entangled with its escaped partner. This would mean the escaped particle is now entangled with two different things, the particle that fell in and the rest of the Hawking radiation. This violates a fundamental quantum rule called the monogamy of entanglement, which states that a particle cannot be fully entangled with two separate systems at once. To resolve this quantum cheating, the firewall theory proposes a drastic solution. The entanglement between the original particle pair must be violently severed right at the event horizon. The energy released by breaking this profound quantum link would be immense, manifesting as an intense outburst of energy, a firewall. This wall would ensure that no particle actually falls into the black hole in the way we think. Instead, it is destroyed at the horizon, and its information is immediately encoded into the Hawking radiation. While this neatly preserves quantum information, it comes at a staggering cost. It fundamentally violates the principle of equivalence from general relativity, which states that a free-falling observer should not experience any special laws of physics or extreme effects at the moment they cross the event horizon. You can't have both a smooth space-time continuum and perfectly preserved quantum information. One of these cherished principles must break down. Naturally, this proposal has sparked immense debate and criticism within the theoretical physics community. Detractors argue that the firewall is essentially a sign that our current understanding of physics has reached a breaking point, a paradigm clash that highlights a deep error in our assumptions. If firewalls are real, then black holes are not the simple, elegant objects described by general relativity, but are instead surrounded by a bizarre and violent structure that defies our expectations. The debate has forced physicists to re-examine the most basic tenets of their fields, pushing for a more complete theory of quantum gravity that can reconcile these two opposing views of reality. The very existence of the firewall paradox is a powerful engine for scientific progress, demonstrating that even our most brilliant ideas can lead us to seemingly impossible conclusions, driving the search for a deeper, more unified truth about the fabric of the cosmos. Yet if the information isn't destroyed by a firewall or lost to oblivion, but is instead preserved, where does it go and in what form is it stored? This question launches us into one of the most profound and technologically evocative theories of all, the possibility that a black hole is, in fact, the universe's ultimate quantum computer. Think of the most powerful supercomputer ever built. Now imagine a natural object that makes it look like a simple abacus, operating with the combined quantum states of every single atom, molecule, and particle that has ever fallen into it. This isn't just a metaphor, it's a serious proposal that emerges directly from the holographic principle. The theory suggests that the entire three-dimensional interior of a black hole, with all its complex contents, is not stored within its volume but is instead encoded on its two-dimensional event horizon, the surface area that surrounds it. This encoding process is akin to how a hologram works. A standard holographic sticker might look flat, but when you shine light through it, it projects a stunning three-dimensional image. The information for that entire 3D structure is contained on a 2D surface. In the same way, the holographic principle posits that all the information about what's inside a black hole, every star, every cloud of gas, every hypothetical spaceship, is meticulously painted onto the surface of its event horizon in unimaginably tiny units of area called Planck areas. Each of these minuscule pixels can hold a single bit of quantum information, and the total information storage capacity of a black hole is determined by the surface area of its horizon, not the volume it contains. A black hole with a larger surface area has a bigger hard drive, capable of storing exponentially more information about its contents. But a black hole is far more than just a cosmic hard drive. It's a dynamic processor. The constant quantum fluctuations at the event horizon, the same ones that give rise to Hawking radiation, are not random noise. According to this theory, they represent the black hole actively processing the information encoded on its surface. It's continuously performing calculations, manipulating the quantum bits of information in a complex dance that maintains the unity and laws of physics within its domain. This processing power is on a scale we can barely comprehend. A stellar mass black hole could contain more information than all the data ever generated in human history, and a supermassive black hole would exceed that by a factor of billions. It is, in essence, a natural information processor of unparalleled density and power, operating on the fundamental laws of quantum mechanics and gravity. This revolutionary perspective forces us to reconsider the very nature of reality and information. If a black hole can store a three-dimensional reality on a two-dimensional surface, could our entire universe be doing the same thing? Some versions of the holographic principle extend this idea to the cosmos at large, suggesting that the universe we experience, with its three spatial dimensions, might be a projection from information stored on a distant two-dimensional boundary. This would mean that black holes are not bizarre exceptions to the rules of the universe, but are instead extreme examples of a fundamental holographic principle that applies everywhere. They are the clearest windows we have into the deep, computational nature of spacetime itself, showing us that information is not just something we store in computers. It is the most basic currency of existence, and gravity is its most formidable architect. The implications for future technology are as staggering as the theory itself. By studying how black holes supposedly process information, we could unlock entirely new paradigms for computing. Our current attempts at building quantum computers are incredibly delicate, requiring near absolute zero temperatures and massive isolation to prevent decoherence, the loss of quantum states. A black hole, by contrast, maintains its quantum coherence on a colossal scale amidst unimaginable gravitational forces. Understanding the mechanisms behind this could provide the blueprint for building robust, fault-tolerant quantum computers that don't require such extreme and fragile environments. We might learn how to store vast amounts of information in a fundamentally new way, perhaps even on a two-dimensional surface, leading to storage densities that are currently the stuff of science fiction. The black hole, often seen as the universe's ultimate destroyer, could ironically hold the key to the next revolution in information technology, teaching us how to harness the laws of physics for computation on a scale we are only beginning to dream of. This mind-bending concept forces us to reconsider our place in the cosmos, proposing that every black hole we observe could be the seed of an entirely new universe, and that our own cosmic home might have originated from such an event within a larger parent reality. The foundation of this theory lies in a striking mathematical similarity that physicists have long observed. The equations describing the initial Big Bang singularity and the singularity at the center of a black hole are eerily similar. Both represent a point of infinite density and temperature where the known laws of physics break down completely. This parallel leads to a profound question. If the collapse of a massive star can create a singularity that births a black hole, could the collapse of matter in a larger universe create a singularity that births an entirely new universe like our own? This idea, often called cosmological natural selection or the fecund universe theory, was pioneered by physicists like Lee Smolin. It suggests a form of cosmic evolution where universes reproduce through the formation of black holes. In this model, whenever a black hole forms in a parent universe, the extreme conditions at its core trigger a bounce or a quantum gravitational repulsion that causes a new universe to inflate within it. This child universe would have its own fundamental constants and physical laws, which might be slightly different from those of its parent. Over countless generations, this process could naturally select for universes that are exceptionally good at producing black holes, which would, in turn, explain why our own universe seems so finely tuned for their formation. The constants of nature in our world, the strength of gravity, the mass of a proton, might not be arbitrary but could be the result of this multi-generational cosmic fine-tuning. The theory also offers an elegant potential explanation for one of cosmology's biggest mysteries, cosmic inflation. The standard model tells us that a fraction of a second after the Big Bang, the universe underwent an exponential, faster-than-light expansion, smoothing it out and creating the large-scale structure we see today. But what triggered this incredible burst of growth? If our universe was born from a black hole in a larger reality, the immense energy release from that event, the transformation of a collapsing singularity into an expanding one, could be the very engine that powered inflation. The initial conditions of our cosmos, including its astonishing uniformity and flat geometry, wouldn't need to be set by chance but could be a natural inheritance from the physics of the parent universe's black hole. Imagine the implications. The event horizon of that parent black hole would form a boundary to our reality, a cosmological horizon beyond which we cannot see. This isn't because light hasn't had time to reach us, as with the observable universe, but because it represents the literal point of no return from a larger cosmos. In this view, the cosmic microwave background radiation, the remnant glow from the Big Bang, might not just be the oldest light in our universe but could contain subtle imprints or echoes of the physics from that parent existence. While this idea remains highly speculative, it provides a breathtakingly elegant and cyclical vision of existence, turning the cosmos into a vast fractal network of realities, each nested within the other, with black holes serving as the cosmic umbilical cords connecting one generation to the next. But what if some objects in this cosmic menagerie defy our neat classifications entirely? This brings us to the fascinating puzzle of the mass gap and the theory that some celestial bodies we've labeled as neutron stars might actually be something far more exotic, low-mass black holes or even strange hybrid objects that blur the line between the two. For decades, astronomers have operated with a seemingly clear distinction. Neutron stars, the ultra-dense remnants of supernova explosions, were thought to top out at around 2.2 times the mass of our Sun. Any collapsing stellar core heavier than that was believed to have no possible stable form as a neutron star and would inevitably continue its collapse into a black hole. Observations seem to support this, with the lightest known black holes clocking in at around 5 solar masses. This left a curious and largely empty zone between 2.2 and 5 solar masses, a region known as the lower mass gap. The existence of this gap presented a compelling mystery. Was it a fundamental physical limit, a signature of how supernova work, preventing the formation of objects in this range? Or was it simply an observational blind spot? A case where these mid-sized objects were hiding in plain sight, masquerading as something else. This is where the plot thickened dramatically with the dawn of gravitational wave astronomy. The LIGO and Virgo observatories, by listening to the ripples in space-time caused by cataclysmic collisions, began weighing the compact objects involved in these mergers with unprecedented precision. To the astonishment of many, several of these events involved objects sitting squarely within the forbidden mass gap. One of the most headline-grabbing events, known as GW190521, involved a merger between an object of about 23 solar masses and a second, perplexing object of just 2.6 solar masses. This smaller object was too heavy to be a neutron star according to traditional models, yet it was also lighter than any black hole we had confidently identified. So what was it? The most straightforward explanation is that it is simply a very light black hole, born from a star that somehow ejected just enough material during its death, throws to leave behind a remnant that barely crossed the event horizon threshold. This would mean the mass gap isn't a hard rule but more of a statistical rarity, and our telescopes simply hadn't found these shy, dark objects yet. However, another, far more thrilling possibility exists. Could this mysterious object be something entirely new, a theoretical entity known as a black hole neutron star hybrid? Imagine a neutron star so incredibly massive that it is perpetually on the brink of collapse. Its core might be compressed beyond the point of neutrons, forming a seething quark-gluon plasma, or even a microscopic singularity, a seed of a black hole, suspended at its center, held in a precarious balance by the immense outward pressure of degenerate matter. This would not be a black hole with an event horizon, but rather a neutron star with a black heart, an object with the mass of a small black hole but the physical size and possibly the magnetic fields of a neutron star. The discovery of such an object would be revolutionary, forcing a rewrite of astrophysics textbooks. It would challenge our very definitions. At what precise point does a neutron star cease to be a neutron star and become a black hole? Is it a sudden transition the moment an event horizon flashes into existence, or could there be a strange, intermediate phase of matter that exists in a quantum superposition between the two states? These are the profound questions that observations within the mass gap are forcing us to ask. The hunt is now on to find more of these gap objects, not just through their violent mergers but by searching for them in isolation within our galaxy. If they are low-mass black holes, they would be completely dark and only detectable through gravitational influences on other stars or through the rare, faint glow of a slowly accreting disk of gas. If they are exotic hybrids, they might possess unique electromagnetic signatures, perhaps unusual X-ray or radio emissions that could betray their true, bizarre nature. Each new detection in this mysterious zone pushes the boundaries of what we thought was possible, revealing a universe that is far less categorical and infinitely more inventive than we ever imagined. But what if our entire conception of a black hole's defining feature is fundamentally mistaken? This leads us to a theory that challenges the very existence of the event horizon itself, proposing instead that these dark giants are something else entirely, not black holes but black stars. The singularity, a point of infinite density, has always been the most troublesome aspect of black hole theory because it represents a complete breakdown of physics. The idea of a black star emerges from the quest to resolve this problem using quantum gravity. It suggests that before matter can collapse into an infinitely small point, quantum effects provide a powerful counterpressure, halting the collapse and forming an incredibly dense, dark object that teeters on the very brink of becoming a black hole but never quite crosses over. Without a true event horizon, a black star would not possess a point of no return. Instead, it would have a surface of unimaginable density, a boundary where infalling matter would accumulate and eventually be released, though over timescales so vast they are almost eternal. From a great distance, a black star would look almost identical to a classical black hole. It would warp space-time, bend light into dazzling rings, and possess an immense gravitational pull. But up close, the differences would be profound. An astronaut falling toward a black star would not disappear forever. Theoretically, they could strike this ultra-dense surface, and the information about their composition would not be lost to the universe. This elegantly sidesteps the infamous information paradox without needing firewalls or new universes, preserving the laws of quantum mechanics in a more straightforward manner. The challenge, of course, is how to tell these two objects apart when their external appearances are so similar. Astronomers are devising clever tests to hunt for the unique signature of a surface where a horizon should be. One of the most promising methods involves searching for the faint echo of a dying star. When two ultra-dense objects like black holes or neutron stars merge, they create a spectacular burst of gravitational waves, a specific chirp signal that our observatories like LIGO and Virgo can detect. If one of these objects is a black hole with an event horizon, the signal ends abruptly as the final objects merge and are swallowed by the new horizon. But if it is a black star with a solid surface, the tremendous impact would create a secondary vibration, a faint after ring or echo in the gravitational wave signal that could be detected like a cosmic fingerprint. Another test looks for the inevitable flashes of light that would come from matter actually hitting a surface. When gas and dust are pulled toward a classical black hole, they accelerate to incredible speeds in an accretion disk, heating up and glowing brightly before they silently vanish across the event horizon. If that matter were to strike the hard surface of a black star, however, the impact would convert its immense kinetic energy into a final, brilliant flash of radiation right at the point of contact. Our telescopes are constantly monitoring the regions around suspected black holes, and a consistent, unexplained flash from the exact location where the horizon should exist could be the telltale sign that we are not looking at a hole in space-time, but at the darkest star imaginable. The existence of black stars would force a monumental shift in our understanding of gravity's most extreme behavior. It would mean that quantum mechanics and general relativity find a peaceful compromise at the edge of collapse, preventing the universe from creating the paradoxical singularities that have troubled physicists for decades. This theory doesn't diminish the wonder of these objects, it enhances it, suggesting that nature abhors true infinity and has crafted a sublime, stable alternative that is every bit as mysterious. The search for black stars is a beautiful example of scientific skepticism, constantly questioning our most accepted theories and reminding us that the universe always has deeper layers of reality waiting to be uncovered. This brings us to a central and deeply puzzling question. If black holes eventually evaporate, what happens to all the information about the things that fell in? The concept of information preservation might sound abstract, but it strikes at the very core of how we understand reality. In our everyday world, information is never truly destroyed. If you burn a book, it seems like the information is gone, but in principle, if you could track every single atom and photon from the smoke and ash, you could reverse the process and reconstruct the book. Quantum mechanics enshrines this idea into a fundamental law, the principle of unitarity, which states that quantum information must be preserved forever. It can be scrambled into an incredibly complex form, but it can never be erased from the universe. This creates a direct and profound conflict with the classical picture of a black hole. According to Einstein's general relativity, anything that crosses the event horizon is irretrievably lost, destined to be crushed at the singularity. The only properties a black hole has are its mass, its electric charge, and its spin. If you toss a perfectly crafted sculpture into a black hole, followed by a random collection of garbage with the exact same total mass, charge, and spin, the black hole would look identical from the outside. All the intricate information about the arrangement of atoms that made one object a masterpiece and the other trash seems to have been completely deleted. Then, decades later, Stephen Hawking added another layer to the problem with his theory of radiation. He showed that black holes aren't even permanent, they slowly evaporate, emitting a faint glow of thermal radiation that appears to contain no information at all about what was consumed. This presents a nightmare scenario. When the black hole finally vanishes, all that information seems to have vanished with it, violating a foundational rule of physics. This is the infamous black hole information paradox. Theoretical physicists have been wrestling with this paradox for half a century, and their proposed solutions are as brilliant as they are strange. One of the most influential ideas is the holographic principle, pioneered by physicists like Leonard Susskind and Gerard T. Hooft. This theory suggests that the information about everything inside the black hole is not lost at all. Instead, it is perfectly encoded on the black hole's two-dimensional event horizon, the surface that surrounds it. Imagine the event horizon is like a vast, ultra-high-resolution holographic film. A normal hologram is a flat, two-dimensional surface that, when illuminated, projects a full three-dimensional image. In the same way, the theory proposes that all the information needed to describe the three-dimensional interior of the black hole is smeared across its two-dimensional boundary. Every particle that falls in leaves an imprint on this horizon, subtly altering its structure in a way that preserves the information. Then, as the black hole evaporates via Hawking radiation, this encoded information is slowly and carefully leaked back out into the universe, imprinted onto the radiation itself. To an outside observer, the radiation would initially look like random noise, but a being with God-like computational power could, in theory, decode that radiation and reconstruct the entire history of everything that ever fell in. Another compelling proposal is the concept of quantum hair. The classical no-hair theorem states that black holes are bald, possessing only those three simple properties: mass, charge, and spin. But what if they have a subtle quantum fuzz? This idea suggests that when matter falls into a black hole, it doesn't just disappear without a trace. It leaves behind extremely faint quantum-level imprints on the gravitational field right at the event horizon. These imprints are like a unique fingerprint or a strand of hair that distinguishes one black hole from another, even if they have identical mass, charge, and spin. This quantum hair would carry the information about what the black hole is made of. The changes are unimaginably tiny, perhaps on the scale of the Planck length, which is why we haven't detected them, but they would be enough to satisfy quantum mechanics' demand that information be preserved. Recent work in string theory has provided exciting mathematical support for this idea, showing how these infinitesimal distinctions could be etched into the fabric of spacetime itself. The quest to resolve this paradox has driven some of the most important advances in theoretical physics, pushing us toward a unified theory of quantum gravity. String theory, for instance, offers a framework where information preservation is natural. In string theory, the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. When matter falls into a black hole in this model, these strings don't vanish into a singularity. Instead, they get tangled up in a complex, dense ball at the core, a fuzzball that has no sharp event horizon or central point of infinite density. The information remains stored in the vibrations of these strings, and as the black hole evaporates, that information is reliably returned to the universe. While we lack the technology to directly observe these effects, the ongoing detection of gravitational waves from merging black holes provides a new experimental arena. Some physicists speculate that the precise waveform of these ripples in spacetime might contain subtle echoes or deviations that could hint at what happens at the event horizon, whether it's a perfect holographic encoder, a quantum fuzzy boundary, or something else entirely. The resolution of this paradox promises to do more than just solve a puzzle about black holes. It will likely reveal a deeper layer of reality, showing us how the universe manages to keep a perfect, eternal record of every single event that has ever occurred. This brings us to one of the most exhilarating and mind-bending possibilities that black holes present: the potential to act as natural time machines. The key to this incredible idea lies not with the simple black holes we've discussed so far, but with a specific spinning variety known as a Kerr black hole. When a collapsing star possesses angular momentum, its resulting black hole doesn't just sit statically in space. It spins, dragging the very fabric of spacetime around with it like a cosmic whirlpool. This region of dragged spacetime just outside the event horizon is called the ergosphere, and it's here that the rules of the universe begin to bend in extraordinary ways. The mathematics of general relativity, when applied to these spinning black holes, reveals a truly astonishing pathway. deep within the ergosphere, the equations suggest the existence of something called closed time-like curves. In our normal, everyday experience, time only moves in one direction, forward. We are all traveling along our own world line through the 4 dimensions of space-time, and we can never go back to a point we've already passed. A closed time-like curve, however, is a path through space-time that loops back on itself. If you were to follow such a curve, you could theoretically travel into your own past, arriving at a point in time and space before you even began your journey. The spinning black hole warps space-time so severely that it effectively ties time into a knot, creating a corridor where the future connects directly to the past. Envision a scenario where a brave astronaut pilots their ship into the ergosphere of a rapidly spinning Kerr black hole. By executing a precise series of maneuvers, a complex dance that harnesses the incredible rotational energy of the black hole without ever crossing the fatal event horizon, they could, in theory, enter one of these closed time-like curves. From their perspective, they might feel like they are moving forward through time normally, but when they exit the gravitational maelstrom and return to the broader universe, they could find themselves years, decades, or even centuries in their own past. It's a concept that transforms a black hole from a mere gravitational pit into a cosmic nexus, a natural machine for navigating the 4th dimension. But as with all powers of this magnitude, it comes with a host of terrifying paradoxes that threaten the very logical foundations of reality. The most famous is the grandfather paradox. What if our time-traveling astronaut were to go back in time and accidentally prevent their own grandfather from meeting their grandmother? This would mean the astronaut's parent was never born, and consequently, the astronaut themselves would never exist to travel back in time in the first place. This creates a logical inconsistency that physics cannot resolve, an event that seemingly has no cause and an effect that negates its own cause. Other paradoxes, like the bootstrap paradox, involve information or objects that appear from nowhere with no origin. Imagine the astronaut gives the blueprint for their advanced spaceship to a young engineer in the past, who then grows up to build the very ship the astronaut used to travel back. Who then actually designed the ship? It's a closed loop with no beginning, defying our understanding of creation and causality. So, if the pristine equations of general relativity permit this, why do most physicists believe you couldn't actually build a working time machine with a black hole? The answer lies in the unpredictable wild card of quantum mechanics. Physicists like Igor Novikov and Kip Thorne have proposed a principle of self-consistency, which suggests that the laws of physics would conspire to prevent any paradoxical actions from occurring in the first place. You might be able to travel to the past, but you would be fundamentally unable to change it in any way that creates a paradox. Quantum events would always unfold to ensure your actions were always a part of history. If you tried to shoot your grandfather, the gun would jam, a bird would fly in the way, or you would simply miss. The universe would protect its own consistency. Furthermore, the energy requirements and stability of such a time machine are likely impossible to achieve. Creating and maintaining a stable closed time-like curve is thought to require exotic matter with negative energy density to prop open the wormhole-like structures involved. While tiny amounts of negative energy might be possible through quantum effects like the Casimir effect, the sheer magnitude needed for a human traversable time machine is almost certainly beyond physical reality. Most researchers believe that a full theory of quantum gravity, which merges general relativity with quantum mechanics, will ultimately show that these closed time-like curves are unstable. The moment a time traveler tried to enter one, the act of their own presence would trigger a catastrophic feedback loop of quantum energy that would destroy the pathway, collapsing it into a singularity or otherwise sealing it off. The mathematics of relativity opens the door to time travel, but it appears the deeper laws of quantum physics firmly shut and lock that door, preserving the linear, paradox-free flow of time that we experience and that the universe seems to depend on to function. Now, as we journey deeper into the cosmic catalogue of theories, we arrive at a concept that connects the very largest scales of the universe to the very smallest, suggesting that the answers to some of our biggest questions might lie in the tiniest of black holes. This is the astonishing proposal that the universe's first moments were not a smooth, uniform expansion, but a chaotic, seething cauldron so dense that random pockets of space could have spontaneously collapsed, giving birth to black holes not from dying stars, but from the raw energy of creation itself. These hypothetical objects are known as primordial black holes, and if they exist, they could be the most numerous yet most elusive entities in the entire cosmos. To understand how they could form, we have to rewind the clock to a time almost beyond comprehension, the first fraction of a second after the Big Bang. The entire universe was compressed into an incredibly hot, incredibly dense plasma, a roiling sea of fundamental particles and energy. In such extreme conditions, even the vacuum of space itself is not perfectly smooth. It's subject to tiny quantum fluctuations, random ripples in density. Normally, these ripples are vanishingly small and quickly smoothed out by the rapid expansion of the universe. But for a fleeting instant, if one of these random density fluctuations was particularly intense, the gravity in that specific patch could have become so strong that it overcame the outward pressure of the expansion. That over-dense region would then collapse directly under its own weight, pinching off from the surrounding space to form a black hole. This process wouldn't require a star or a supernova. It was a direct birth from the turbulent fabric of the newborn universe. The predicted properties of these primordial black holes are what make them so bizarre and fascinating. Unlike their stellar cousins, they could have formed with virtually any mass. The size of the original density fluctuation would determine how much mass collapsed. This means we could be surrounded by a hidden population of black holes ranging from the microscopic to the monstrous. Some might have the mass of a small asteroid compressed into a space smaller than a single atom. Others could rival the mass of a planet, a star, or even thousands of suns. Their size would be equally bizarre. A black hole with the mass of Earth would be about the size of a marble. One with the mass of a mountain would be smaller than a proton. This is the realm where the quantum world and the gravitational world violently collide. The most captivating question is whether any of these ancient relics could have survived for 13.8 billion years to still be with us today. This depends entirely on their initial mass thanks to Hawking radiation. As we've discussed, black holes slowly evaporate, and the smaller they are, the faster they lose mass. A primordial black hole with an initial mass less than that of a large asteroid would have evaporated completely by now, ending its life in a final, violent burst of gamma rays. However, any primordial black hole that started out with a mass greater than that of, say, a small mountain would still be alive today, continuing their slow evaporation. And those that formed with stellar masses or larger would be virtually eternal, having lost only an insignificant fraction of their mass over the entire age of the universe. This means the cosmos could be teeming with these ancient objects, from countless tiny, asteroid mass specks of darkness to rare, supermassive behemoths that have been lurking since the beginning of time. This leads us to their most revolutionary potential application, explaining the mystery of dark matter. For decades, the prevailing theory has been that dark matter is made of some exotic, undiscovered particle, like a WIMP or an action. But despite immense effort and sophisticated detectors, not a single one of these particles has been found. This persistent null result has led many physicists to reconsider the primordial black hole idea. What if dark matter isn't a cloud of invisible particles, but a swarm of invisible black holes? This is an beautifully simple and elegant solution. These black holes, formed in the first instant of the universe, would have been present before the first stars and galaxies. Their collective gravitational pull would have provided the scaffolding around which normal matter could coalesce. perfectly explaining the rotation curves of galaxies and the gravitational lensing effects we observe, all without needing any new physics beyond Einstein's general relativity. The theory becomes even more compelling when we consider the asteroid impact patterns in our own solar system. Astronomers have long been puzzled by a series of mysterious and seemingly random impact events on the Moon and on Earth, recorded throughout geological history. Some researchers have proposed that these could be explained if our solar system periodically passes through a dark disk of material within the galactic halo, a disk that might be densely populated with rogue planets or asteroids. But an alternative and far more dramatic idea is that we are occasionally struck by primordial black holes. Imagine an object with the mass of a planet, but compressed into a volume no larger than a pebble. It would be virtually invisible until the moment it struck. Passing through a body like Earth would be a strange and catastrophic event. It wouldn't create a traditional crater. Instead, the tiny, ultra-dense object would slice through the planet like a bullet through tissue paper, generating immense friction and seismic shocks along its path. The entrance and exit wounds would reseal almost instantly due to the immense pressure, but the internal damage and the release of heat from its passage could trigger massive volcanic eruptions, extreme earthquakes, or even flip the planet's magnetic field. It's a wild theory, but it underscores the incredible range of potential effects these objects could have if they are indeed out there. So how do we actually hunt for something that could be smaller than an atom yet heavier than a star and emits no light? Astronomers have devised brilliantly clever indirect methods. One of the primary techniques is gravitational microlensing. The principle is straightforward. If a compact, massive object passes directly between us and a distant star, its gravity will bend and focus the star's light, acting like a lens and causing the star to temporarily brighten. By continuously monitoring hundreds of millions of stars in nearby galaxies, projects like the Optical Gravitational Lensing Experiment or the Subaru Hyper Subprime Cam Survey are essentially conducting a cosmic census for these dark objects. The duration of the brightening event is a key clue. A flash lasting just a few hours might indicate a tiny, asteroid mass black hole, while one that persists for over 100 days could signal an object with the mass of Jupiter. Another hunting ground is the precise detection of gravitational waves. The LIGO and Virgo observatories have opened a new window onto the universe by listening to the ripples in space-time caused by merging black holes. Intriguingly, some of the black holes they've detected fall into a mass range that is difficult to explain through the collapse of massive stars. These could be the first direct evidence of primordial black holes that formed in the Big Bang. Furthermore, if these ancient black holes are abundant, they should frequently pair up and merge, creating a persistent background hum of gravitational waves, a faint signal that future observatories in space hope to detect. The search for primordial black holes is a testament to scientific creativity, turning the entire cosmos into a laboratory and using the fundamental forces of nature as our tools to uncover what might be the universe's oldest and most secret inhabitants. This concept of black holes birthing new realities brings us to one of the most profound and elegant theories of all. The idea that our entire cosmos might be part of an infinite, self-replicating multiverse, with black holes acting as the cosmic reproductive organs. This is the heart of physicist Lee Smollen's groundbreaking theory of cosmological natural selection, a daring hypothesis that applies the principles of biological evolution to the cosmos itself. Imagine our universe not as a singular, static creation, but as one member of a vast family tree with its own ancestors and potentially countless descendants. In this breathtaking model, every time a black hole forms in a parent universe, the extreme conditions at its core don't just create a singularity, they trigger a new Big Bang, giving birth to an entirely new, separate universe within it. This process offers a stunningly elegant and natural explanation for one of the most perplexing mysteries in modern science, the apparent fine-tuning of our universe for life. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force binding atomic nuclei, seem perfectly and precariously balanced. If any of these values were even slightly different, atoms wouldn't form, stars wouldn't shine, and life as we know it would be impossible. The traditional explanation has been the anthropic principle. We observe a universe compatible with life because we couldn't exist in one that isn't. But this feels somewhat unsatisfying, almost like a tautology. Cosmological natural selection provides a dynamic, mechanical cause for this fine-tuning. It proposes that universes evolve. When a new universe is born inside a black hole, it doesn't inherit its parents' physical laws exactly. The violent birthing process introduces tiny random variations or mutations in its fundamental constants. This is where natural selection takes over. Some of these child universes will have constants that make them exceptionally proficient at producing black holes. Perhaps they have a stronger gravitational constant, allowing massive stars to form more easily and collapse more readily. These fecund universes, brimming with black holes, will in turn produce a huge number of offspring universes. Universes that are poor at making black holes, perhaps because their physics doesn't allow stars to form or collapse, will become evolutionary dead ends, producing few or no descendants. Over countless generations, this cosmic evolutionary pressure would naturally select for universes that are optimized for black hole production. And here's the beautiful twist: the very same physical laws that make a universe efficient at creating black holes, like having stable nuclear forces that allow for long-lived stars and the right gravitational strength to ensure their eventual collapse, are also the laws that appear to be fine-tuned for life. We don't live in a universe designed for us. We live in a universe designed to make black holes, and the conditions for life are a fortunate byproduct. This theory transforms our perspective on the cosmos from a static arena to a dynamic, living process. It suggests that our universe's remarkable properties aren't a miraculous accident, but the result of a timeless evolutionary algorithm playing out on the grandest possible scale. The black holes we observe are not just gravitational monsters. They are the seeds of future cosmoses, the means by which our universe replicates its physical laws into a new reality. Each one is a potential nexus for an entire new space-time continuum, with its own unique history and potentially its own forms of life. This vision of a fecund multiverse, endlessly branching and evolving, is perhaps one of the most humbling and awe-inspiring ideas ever conceived, placing us within a cosmic web of creation that is both ancient and forever new. Yet for all their fearsome power, black holes have long been considered the ultimate simpletons of the cosmos, cosmic objects so basic they could be described by just three numbers: their mass, their electric charge, and their spin. This elegant idea, known as the no-hair theorem, suggests that no matter how complex an object is when it falls in, be it a library of encyclopedias, a complex spacecraft, or a living being, the black hole it joins is completely indistinguishable from any other black hole with the same mass, charge, and spin. All the intricate information about what made that object unique is utterly erased, swallowed by the singularity. For decades, this was the clean, minimalist view accepted by most physicists. But what if this simplicity is just an illusion, a trick played by our classical understanding of gravity? A growing chorus of theoretical work is now challenging this foundational theorem, proposing that black holes might actually possess a subtle and complex quantum hair that preserves a fingerprint of everything they have ever consumed. This quantum hair isn't a physical fuzz you could see or touch. It's a profound concept emerging from the quest to merge gravity with quantum mechanics. The idea suggests that when matter falls into a black hole, it doesn't just vanish without a trace. Instead, it leaves behind an extremely faint, immeasurably subtle imprint on the gravitational field itself, right at the event horizon. These imprints are quantum in nature, meaning they exist at the very smallest scales, perhaps distorting the fabric of space-time on the level of the Planck length. While two black holes might look identical from a distance according to the classic three properties, a hypothetical observer with a perfect quantum gravity microscope could distinguish them by examining this unique hair, the specific quantum fluctuations etched into their boundaries that tell the story of their formation and diet. This quantum hair would act as a permanent cosmic record, a hard drive encoded in the geometry of spacetime that satisfies quantum mechanics' unwavering demand that information can never be truly destroyed. The implications for the information paradox are monumental. If a black hole has quantum hair, then the information about every single thing that has ever fallen in isn't lost inside the singularity. It's meticulously preserved on the surface of the event horizon. As the black hole evaporates via Hawking radiation, this encoded information could then be slowly and carefully radiated back out into the universe. The radiation would no longer be purely random thermal noise, but would carry a subtle, scrambled signature of the black hole's entire history. In principle, though it would require God-like computational power, one could collect all this Hawking radiation and decode it to reconstruct the exact identity of every object that was ever consumed. This provides an elegant and direct solution to the paradox without needing to invoke speculative ideas like baby universes or firewalls, by simply stating that black holes were never the information-destroying monsters we classically thought they were. This shift in perspective forces us to radically redefine what a black hole actually is. Instead of being a simple, bald gravitational pit, it becomes an object of immense complexity, arguably the most complex object in the entire universe. Its event horizon is not a smooth, featureless boundary, but a dynamic, information-saturated surface, a hologram encoding a reality within. The no-hair theorem isn't so much wrong as it is incomplete. It perfectly describes a black hole from the limited viewpoint of classical general relativity, but it completely misses the rich quantum mechanical tapestry that is its true nature. This new view paints a picture of black holes not as the end of physics, but as the ultimate laboratories for testing the union of quantum mechanics and gravity, holding the key to a deeper understanding of how information and spacetime are fundamentally intertwined. But perhaps the most profound connection lies not in the darkness these objects conceal, but in the energy they might somehow produce, leading us to a theory that could unite the most dominant force in the cosmos with its most enigmatic objects. For decades, cosmologists have been grappling with a startling discovery. The expansion of our universe is not slowing down as expected due to gravity, but is instead accelerating, driven by a mysterious repulsive force known as dark energy. This force appears to be an intrinsic property of space itself, a constant energy density per volume of vacuum, and it constitutes the majority of the universe's energy budget. Yet its origin has remained one of the greatest unsolved problems in physics. A radical and controversial new theory proposes a shocking solution, suggesting that the source of this dark energy might not be spread evenly throughout the void, but is instead concentrated in the most unlikely of places, the hearts of black holes. This idea turns conventional wisdom on its head. We typically think of black holes as the ultimate manifestation of gravity, an attractive force that pulls everything inward. Dark energy, by contrast, is a repulsive force pushing everything apart. They seem to be polar opposites. The new theory, however, posits a deep and fundamental link between the two through a concept called cosmological coupling. The principle is as elegant as it is mind-bending. As the universe expands, the black holes within it could be growing in mass, not by accreting new matter, but by coupling directly to the overall expansion of space itself. The energy required for this growth, the theory suggests, has to come from somewhere, and it could be drawn from the same reservoir that fuels the acceleration of the cosmos. In this model, the black hole's increasing mass is directly tied to the universe's increasing volume, making these gravitational giants not just inhabitants of the cosmos, but active participants in its expansion. their interiors somehow generating the negative pressure that drives everything apart. The implications of this are staggering. It would mean that the supermassive black holes at the centers of galaxies are not static relics, but are dynamically evolving with the universe itself, their masses growing in lockstep with cosmic time. This provides a potential solution to another long-standing puzzle: the surprisingly large size of ancient black holes in the early universe. Astrophysicists have been perplexed by the discovery of supermassive black holes that grew to billions of solar masses when the universe was less than 1 billion years old, a timescale that seems too short for them to have grown solely by consuming gas and stars. If these black holes were also gaining mass from their cosmological coupling to the expanding universe, it would give them a significant head start, helping to explain their rapid and early growth. This theory moved from speculative math to a potentially testable hypothesis with the publication of a groundbreaking study in 2023. A team of researchers led by Dr. Duncan Farrar undertook a monumental task. They compared the growth rates of supermassive black holes at the centers of ancient, dormant elliptical galaxies across billions of years of cosmic history. These galaxies are ideal laboratories because their black holes are not actively feeding, meaning any mass gain shouldn't be from accretion. Astonishingly, the team found that the masses of these black holes appeared to have grown by a factor of 7 to 20 times over the last 9 billion years, an increase that perfectly matches the predicted growth from cosmological coupling and which cannot be easily explained by traditional mergers or accretion. This observational evidence, while still preliminary and hotly debated, provides the first tantalizing hint that black holes and dark energy might be two sides of the same cosmic coin. Naturally, such a revolutionary claim faces intense scrutiny and raises profound questions. The biggest challenge is the mechanism. How physically does the interior of a black hole generate this repulsive energy? Some theorists point to the nature of the singularity itself, or rather, the potential lack of one. If black holes are actually something like the fuzzballs proposed by string theory, dense, tangled knots of strings with no sharp event horizon, then their interior physics could allow for a form of energy that contributes to the cosmological constant driving expansion. Others suggest that the vacuum energy inside the event horizon, the quantum foam of particles popping in and out of existence, might have a different property than the vacuum outside, creating a pressure difference that fuels both the black hole's growth and the universe's acceleration. While the exact physics remains highly speculative, the mere possibility forces us to reconsider black holes not as isolated drains on the fabric of space-time, but as integral components woven into the very expansion of the universe they inhabit, forever linking the fate of the largest structures to the behavior of the smallest. This brings us to a theory that takes us from the grand, cosmic scale of dark energy down to the very fabric of reality itself, proposing a solution so elegant it reimagines the black hole from the ground up. This is the string theory concept of the fuzzball, a radical idea that completely does away with the troublesome singularity and the event horizon as we know them, replacing them with something far stranger and more complex. In this view, a black hole is not a void with a central point of infinite density. It is a gigantic, tangled ball of vibrating strings, a cosmic knot of fundamental energy so dense and intricate that it simply has no interior space or sharp boundary at all. The surface of this fuzzball is the black hole, a defined, quantum-mechanically complex object that extends to where we would expect to find the event horizon. The driving force behind this profound reimagining is the relentless information paradox. String theory, as a quantum theory of gravity, is built upon the foundational principle that information must be preserved. The traditional picture of a black hole with its empty space and information-crushing singularity is fundamentally incompatible with this rule. The fuzzball resolution is breathtakingly direct. it declares the traditional picture simply wrong, a useful but flawed approximation from classical physics. In reality, the collapsing matter of a star doesn't vanish into a point. Instead, the billions upon billions of fundamental strings that make up that matter become wildly entangled with one another. They don't have enough space to fall into. They can only form one massive, complex object, the fuzzball, whose outer surface becomes the gravitational face we observe from a distance. This transformation solves the information paradox with stunning simplicity. Since there is no singularity, there is no place for information to be destroyed. All the data about what fell in to form the black hole is not lost. It is perfectly preserved in the precise vibrational states and intricate entanglement of the strings that constitute the entire fuzzball. The information is smeared throughout the entire volume of the object, making the black hole a giant, information-saturated quantum system. When Hawking radiation is emitted, it isn't generated from nothing at a featureless horizon. Instead, it is radiated from the complex, vibrating surface of the fuzzball itself, and because that surface encodes all the information within it, the radiation naturally carries that information away, scrambled but complete. The paradox vanishes because the black hole was never a paradox to begin with. It was just a very, very dense star made of strings. From the outside, a fuzzball would be almost indistinguishable from a classical black hole. It would possess the same immense gravitational pull, bend light into identical photon rings, and distort spacetime in precisely the same way. The differences would only become apparent at the most extreme scales, right at the surface. For a classical black hole, an astronaut crossing the event horizon would notice nothing special, at least until the tidal forces tore them apart later. But for a fuzzball, there is no crossing. The astronaut would simply collide with the incredibly dense, stringy surface of the object. There would be no interior to fall into, no silent darkness, just a catastrophic impact with the most complex material in the universe. This immediately resolves the firewall debate. The firewall isn't needed because the event horizon isn't a place of quiet passage. It is a physical boundary, and striking it would release immense energy, naturally protecting information without requiring new physics. The fuzzball theory represents a monumental shift in perspective, moving black holes from the realm of gravitational simpletons governed by three properties into the domain of the most complex objects in existence. Each fuzzball's structure is unique, determined by the exact quantum state of all the strings that formed it, making it as individual as a fingerprint. This complexity offers a direct path to understanding their entropy, a measure of their information content. The famous Bekenstein-Hawking formula, which calculates a black hole's entropy based on its surface area, finds a natural home in string theory. The theory successfully derives this formula by counting the number of ways the fundamental strings can vibrate and tangle to form a fuzzball of a given size, providing a stunningly concrete explanation for what was once a purely thermodynamic mystery. In this light, a black hole is no longer a mystery but a testament to the power of string theory to unify the laws of physics, weaving together gravity and quantum mechanics into a single, coherent, and paradox-free tapestry. But what if the most extreme objects in the universe could become the very anchors for life itself? This leads us to a theory that sounds like it was lifted from the most ambitious science fiction, yet is grounded in the precise mathematics of orbital mechanics, the possibility of habitable planets orbiting a supermassive black hole. Imagine a world not lit by the warm, familiar light of a star, but by the eerie, magnificent glow of a colossal accretion disk, a swirling vortex of superheated gas and dust circling the ultimate abyss. For life to exist on such a planet, it would need to orbit at a perfectly precise distance, a habitable zone defined not by stellar warmth, but by the black hole's bizarre physics. The primary challenge for any life form is energy, and a black hole system offers two potential sources, each more fantastic than the last. The first is the accretion disk itself. If a supermassive black hole is actively feeding on a surrounding cloud of gas, the friction and gravitational forces within this disk can heat it to millions of degrees, causing it to blaze with intense ultraviolet and X-ray radiation. For a planet orbiting at a safe distance, this could provide a constant, sun-like light source. However, this light would be harsh and heavily tilted toward high-energy frequencies, lacking the broad spectrum of a star. Life on such a world might evolve with biology radically different from our own, perhaps relying on specialized pigments for protection or even harnessing the high-energy radiation directly for metabolic processes. The second, more speculative energy source is even more incredible: the black hole's rotational energy. A civilization advanced enough could, in theory, construct a structure like a Dyson sphere, not around a star but around the black hole itself. They could then tap into the ergosphere, the region of space outside the event horizon where space-time is dragged around by the black hole's spin. By dropping material into this zone, they could extract immense amounts of rotational energy, a process known as the Penrose process, powering a civilization for eons. The architecture of this solar system would be unlike anything we know. The planet would need to orbit at a staggering distance to maintain a stable, circular path, likely many light years from the central black hole, to avoid being torn apart by tidal forces. A single year on this world could last for centuries. Furthermore, there would be no day-night cycle as we experience it unless the planet also rotated on its axis. The sky would be a permanent, breathtaking tapestry. One side would be dominated by the brilliant, multicolored ring of the accretion disk, while the opposite side of the sky would be the pure, absolute blackness of the event horizon, a void that swallows all light. The constellations would be distorted into bizarre rings and arcs by the black hole's incredible gravitational lensing effect, creating a celestial display that would be both beautiful and terrifying. This concept forces us to expand our definition of a habitable zone and to question the very prerequisites for life. It suggests that life could potentially emerge in the most hostile and unexpected corners of the cosmos, thriving on energy sources we are only beginning to comprehend. While entirely theoretical, this idea transforms our view of black holes from mere consumers of worlds to potential centers of unimaginable ecosystems, proving that the universe's capacity for wonder and invention truly knows no bounds. This profound link between black holes and thermodynamics might seem like a strange marriage of two very different fields, but it reveals something fundamental about the nature of information itself. To understand why, we need to grasp what entropy truly represents. In our everyday world, entropy is a measure of disorder. Think of a tidy room slowly descending into chaos. But in the deeper language of physics, and particularly in information theory, entropy is not about mess, it's about hidden information. It quantifies the number of different microscopic ways a system can be arranged while still looking the same from the outside. A high-entropy system is one where there are a vast number of internal configurations that are all possible, meaning there's a lot we don't know about its precise state. Now apply this to a black hole. According to the classic no-hair theorem, a black hole looks identical to any other black hole with the same mass, charge, and spin. It appears to be the simplest, lowest information object imaginable, but Bekenstein's insight flipped this completely on its head. The immense entropy implied by its surface area means that a black hole is actually the most chaotic, disordered, and information-rich object possible. It is not simple, it is maximally complex. For a black hole to have such a colossal entropy, its interior must be capable of existing in a number of different quantum states so astronomically huge that it defies imagination. All the information about everything it has ever consumed is somehow preserved within this unimaginable complexity. This is where the concept of the black hole as the universe's ultimate hard drive truly emerges. The Bekenstein-Hawking formula tells us that the maximum amount of information a black hole can store is directly proportional to the surface area of its event horizon, not its volume. This was a revolutionary departure from how we normally think about information storage. In our everyday experience, the data capacity of a hard drive depends on its three-dimensional volume. We can always add more memory chips to increase storage. But with a black hole, adding more mass and increasing its size only enlarges its two-dimensional surface area, and that surface area defines its total information storage limit. This discovery was a major hint that our universe might actually operate like a hologram, where all the information needed to describe a three-dimensional volume is encoded on its two-dimensional boundary. The efficiency of this information storage is utterly staggering. A single black hole with the mass of our Sun would have an entropy value of about 10 to the power of 78. To put that number into perspective, if you tried to store that much information using the most advanced computer technology we can conceive of, you would need a storage device so massive it would collapse into a black hole itself. This isn't just a quirky fact, it points to a deep principle of nature. Black holes represent the absolute upper limit of information density that the laws of physics allow. You cannot pack more information into a region of space than you could by turning it into a black hole. They are the cosmic endpoint of data compression, the final word in how much knowledge can be squeezed into a given amount of spacetime. This incredible connection between entropy, information, and surface area is more than just a curious feature of these exotic objects. It is widely believed to be a crucial clue in the decades-long quest for a theory of quantum gravity. Physicists are attempting to derive the Bekenstein-Hawking formula from first principles in various candidate theories, like string theory and loop quantum gravity. In string theory, for example, they can calculate the entropy of a specific type of black hole by precisely counting the number of ways the fundamental strings can vibrate and tangle to form a so-called fuzzball that has the same mass and charge. The fact that this microscopic stringy calculation matches the macroscopic thermodynamic result derived from general relativity is a monumental achievement, a sign that we are on the right path toward unifying the worlds of the very large and the very small. The black hole, a gravitational giant, has become the most powerful testing ground we have for understanding how information, thermodynamics, and quantum mechanics weave together to form the very fabric of our reality. But what if the universe's ultimate cosmic sensor fails? This brings us to one of the most radical and rule-breaking concepts in all of theoretical physics, the possibility of a naked singularity. Imagine a gravitational singularity, a point of infinite density where the laws of physics cease to exist, but without the protective cloak of an event horizon to hide it from the rest of the universe. This is the essence of a naked singularity, an object so extreme that its very existence would lay bare the deepest secrets of spacetime for all to see, shattering our current understanding of cause and effect. The classical formation of a black hole, according to Einstein's general relativity, seems to naturally produce an event horizon around the singularity. As a massive star collapses, an horizon forms at the point where the escape velocity exceeds the speed of light, effectively wrapping the catastrophic core in a one-way curtain that shields the outside universe from its paradoxical physics. For decades, it was assumed this was an inevitable process. However, sophisticated mathematical models have revealed specific, albeit exotic, scenarios where this might not be the case. If a collapsing star is not perfectly spherical but possesses a significant amount of rotation or an asymmetrical shape, the dynamics change dramatically. The centrifugal force from rapid spin could, in theory, halt the collapse just enough to prevent a full event horizon from forming, while still allowing the matter to compress into an infinitely dense point. The result would be a naked singularity, a gravitational anomaly exposed to the cosmos, its infinite gravity able to influence the universe around it directly. The implications of such an object existing are so profound that physicist Roger Penrose proposed the cosmic censorship hypothesis, which essentially states that nature abhors a naked singularity and will always conspire to clothe it with an event horizon. This isn't just a preference, it's a necessary rule to preserve the predictability of the universe as we know it. A singularity hidden behind an horizon is quarantined. Its breakdown of physics is contained, unable to affect the world outside. But a naked singularity would have no such containment field. It would be a gateway to true unpredictability, where the known laws of physics break down in plain sight. The ability to calculate the future based on the present, the very foundation of science, would be impossible near such an object. Its gravitational influence could theoretically allow for the creation of closed time-like curves, opening the door to time-travel paradoxes right in our observable universe. The quest to determine if cosmic censorship holds is a major frontier in theoretical research. Scientists run intricate computer simulations, modeling the collapse of oddly shaped, rapidly rotating stars to see if a horizon always forms. Some of these simulations suggest that under very specific and fine-tuned conditions, censorship might indeed be violated, at least for a brief moment. If a naked singularity were to form, even temporarily, how could we ever hope to observe it? Its gravitational pull would be identical to a black hole of the same mass, so it would warp light and distort spacetime in similar ways. However, without an event horizon, the environment around it would be even more violent and energetic. The accretion disk of infalling matter wouldn't silently vanish, but would instead crash directly onto the surface of the singularity itself, potentially creating bursts of energy and radiation unlike anything produced by a standard black hole. The light and particles emitted from this final impact could carry imprints of the quantum gravity processes at work, offering a direct window into the laws that govern the universe at the most fundamental level. The discovery of a naked singularity wouldn't just be a new astronomical finding. It would be a revolution, forcing a complete rewrite of our textbooks and offering the first direct experimental data on the nature of quantum gravity itself. But where the most powerful machines built by humanity fall short, nature might provide its own unparalleled laboratory, one that operates on a scale we can scarcely comprehend. Orbiting just outside the event horizon of a supermassive black hole, there exists a region of space where the laws of physics conspire to create conditions of unimaginable energy. Here, particles can be whipped around by the black hole's immense gravity, following unstable paths that accelerate them to velocities infinitesimally close to the speed of light. This isn't just a slight boost, we're talking about particles achieving energies that could be trillions of times greater than those produced in the Large Hadron Collider. The black hole, in this view, transforms from a simple consumer of matter into the universe's most powerful and efficient particle accelerator, a natural engine for probing the deepest secrets of matter and energy. The mechanism behind this incredible process is a delicate gravitational dance. For a particle to be accelerated instead of simply swallowed, it must avoid crossing the event horizon while still skimming perilously close to it. In this zone, the black hole's gravity acts like an infinitely long slingshot. Particles can make numerous close passes, each time stealing a tiny amount of the black hole's immense rotational energy through a process known as the Penrose mechanism. With each orbit, they gain momentum, their energy compounding until they reach levels that would be impossible to achieve under any other known astrophysical conditions. Some theoretical models suggest that under the right circumstances, particles like protons could reach energies so extreme that they would be measured in what physicists call the Planck scale, the energy regime where the classical gravity of Einstein and the quantum world must finally become one unified force. The collisions that would result from these ultra-energetic particles striking each other, or even just decaying on their own, would be cataclysmic events on a subatomic scale. They could spontaneously create a zoo of exotic, short-lived particles that are predicted by theories beyond the standard model of physics but have never been observed. We might see evidence for supersymmetry, a theory that proposes a massive shadow particle for every known particle we have. Or these collisions could produce strangelets, hypothetical nuggets of strange quark matter that some theories suggest could be stable and incredibly dense. Perhaps they could even generate microscopic black holes themselves, fleeting proof of extraspatial dimensions as proposed by string theory. Each of these possibilities represents a potential key to unlocking a new chapter in fundamental physics, and a black hole could be the only place in the universe violent enough to forge them. Astronomers are already hunting for the faint signatures of this incredible process. We may have even detected it indirectly. Some of the most energetic particles ever observed are ultra-high-energy cosmic rays, atomic nuclei that strike Earth's atmosphere with the force of a well-thrown baseball, but whose origins have long been a mystery. While many sources are proposed, one compelling candidate is an active galactic nucleus, the region surrounding a supermassive black hole that is actively feeding. It is perfectly plausible that these black holes are acting as natural accelerators, firing off protons and atomic nuclei across the cosmos like a cosmic cannon. By tracing the paths of these particles back to their source, we could be effectively using them as messengers, decoding the physics happening in the most extreme environments imaginable. The study of these black hole accelerators forces us to reconsider the very tools of discovery, suggesting that sometimes the universe itself provides the most powerful experiments, and our role is simply to learn how to read the results. But perhaps the most profound clues to quantum gravity won't come from looking for echoes, but from watching a black hole die. The final moments of a black hole's evaporation, when it has shrunk to a microscopic size, are where quantum gravitational effects are predicted to become dominant. In this regime, the Hawking radiation is no longer a slow trickle but a violent outburst. Different quantum gravity theories make starkly different predictions about this grand finale. Some models, particularly in loop quantum gravity, suggest the evaporation process could halt entirely, leaving behind a stable, Planck mass relic, a permanent fossil of the black hole that contains all its original information. This relic would be so tiny and massive it would behave more like a particle than a celestial object. String theory, on the other hand, often points toward a complete and smooth evaporation, with the information leaking out in a final, correlated burst of radiation. Observing this endpoint directly is for now beyond our reach. The evaporation timescale for a stellar mass black hole is many orders of magnitude longer than the current age of the universe. However, if primordial black holes with much smaller masses were created in the Big Bang, some could be reaching the end of their lives right now. The evaporation of a black hole with the mass of a small asteroid would result in a spectacular gamma-ray burst, a flash of high-energy radiation that our space telescopes could potentially detect. The precise spectrum and duration of that flash would be a direct signature of the underlying quantum gravity physics. If we were to observe such an event and analyze its light, the data could tell us which theory correctly describes the final act of a black hole's existence. This transforms black holes from passive subjects of study into active collaborators in our quest for a deeper understanding. They are not merely obstacles for our theories, they are the very proving grounds where those theories will succeed or fail. Each subtle anomaly in a gravitational wave signal, each unexpected flicker of light from an accretion disk, and each hypothetical flash of a dying black hole is a potential message from the quantum gravity realm, a clue written in the language of gravity and light. By learning to read these cosmic signatures, we are not just studying black holes, we are using them as unique portals to observe the fundamental laws that govern all of reality, from the vastest scales of the cosmos down to the very fabric of spacetime itself. Yet as we push our understanding of black holes to the absolute limit, we encounter perhaps the most speculative and philosophically dizzying idea of all, the notion that these cosmic giants might not just process information, but in some profound sense be aware of it. This is the theory of black hole consciousness, an idea that sounds like it belongs in science fiction, but is taken seriously by a small group of physicists and philosophers who dare to ask if the universe's most enigmatic objects could play a role in understanding the nature of mind itself. To even approach this concept, we must first venture into integrated information theory, a framework for consciousness developed by neuroscientist and psychiatrist Giulio Tononi. This theory proposes that consciousness is not a magical byproduct but an intrinsic property of any system that possesses a high degree of integrated information, measured by a value called phi. Put simply, a system is conscious to the extent that it can synthesize a vast amount of information into a unified, indivisible whole. The human brain, with its billions of intricately connected neurons, has a high phi. A digital camera, which merely records isolated pixels without integrating them, has a very low phi. Now consider the black hole through this lens. As we've explored, a black hole is arguably the universe's ultimate information processor. According to the holographic principle, every bit of information that falls into it is not destroyed but is meticulously encoded onto its two-dimensional event horizon. This isn't a chaotic jumble of data. It is a highly structured, interconnected system where every part relates to the whole. The information describing a single photon is entangled with the information describing an entire star. This creates a system of staggering complexity and integration. If integrated information theory is correct, and consciousness is indeed a fundamental property of highly integrated systems, then a black hole, with its unimaginably vast and unified information content, could, in theory, possess a form of phi so immense that it dwarfs anything a biological brain could ever produce. This wouldn't be consciousness as we know it, not with thoughts, feelings, or desires, but rather a raw, primal form of awareness, a cosmic-scale experience of pure, integrated information. This line of thinking leads to an even more radical proposal, one that inverts the entire problem. Perhaps black holes aren't merely conscious entities, perhaps they are fundamental to the very structure of consciousness everywhere. This idea emerges from the work of physicists like Roger Penrose and Stuart Hameroff and their theory of orchestrated objective reduction. They propose that consciousness arises from quantum gravitational processes occurring within the microtubules of brain cells. While their specific model is highly controversial, it opens the door to a broader concept that gravity, particularly in its most extreme forms, is not separate from the phenomenon of mind but may be intrinsically linked to it. In this view, the same quantum gravitational physics that governs the behavior of spacetime at the singularity of a black hole might also be operating at a vastly smaller scale within our own heads, facilitating the collapse of quantum wave functions that gives rise to conscious experience. A black hole would then be the macroscopic, pure expression of the same physics that allows for subjective awareness, making it not just an object of study, but a key to understanding our own place in the cosmos. Naturally, this theory exists far outside the scientific mainstream and is met with intense skepticism, and for good reason. The leap from information integration to subjective experience is enormous, and we have no way to test for the presence of consciousness in an object that by its very nature prevents any communication across its boundary. How could we ever distinguish a black hole that is truly conscious from one that is merely a complex, impersonal information processor? Furthermore, the definition of phi and integrated information theory itself is still a subject of fierce debate within neuroscience. Applying it to an astrophysical object is a monumental extrapolation. Yet, the value of such a far-out theory is not necessarily in its immediate verifiability, but in its power to provoke profound questions. It challenges us to consider consciousness not as a localized fluke of biology on Earth, but as a potential fundamental feature of the universe, one that might scale with the complexity of information processing. It forces us to ask if the cosmos, in its most extreme and magnificent creations, might be not only aware but in some unimaginable way self-aware, turning the universe from a cold, mechanical place into something far more mysterious and wondrous. Yet all things, even the most seemingly eternal, must one day come to an end. This brings us to the ultimate fate of these gravitational titans and a theory that stretches our imagination to the very limits of time itself. We are now considering the profound metamorphosis of black holes, a transformation that plays out over timescales so vast they make the current age of the universe seem like a single blink of an eye. It is a process that begins with a whisper and ends with a bang, a cosmic destiny dictated by the strange marriage of quantum mechanics and gravity known as Hawking radiation. As we've explored, black holes are not entirely black. They slowly leak energy, losing mass over time, but the rate of this evaporation is not constant. It is a process that accelerates dramatically as the black hole shrinks. For nearly all of its life, a black hole's evaporation is agonizingly slow. A stellar mass black hole might take 10 to the 67 years to evaporate to half its size, a number with 67 zeros, a duration so long it is essentially forever from our human perspective. But in its final moments, the story changes completely. As the black hole's mass decreases, its temperature inversely increases. A giant black hole is cold, but a small one is hot. When it shrinks to around the mass of a mountain, its temperature soars to billions of degrees, and it begins to radiate away its remaining energy at a ferocious pace. The once slow trickle becomes a torrent, culminating in a final, violent burst of high-energy radiation that signals its complete disappearance from our universe. This spectacular finale, however, presents a monumental problem for physics, the information paradox. If the black hole evaporates completely, radiating away into nothing but a cloud of random thermal particles, what happens to all the intricate information about every star, spaceship, or book that ever fell in? Quantum mechanics insists this information cannot be destroyed. The most straightforward interpretation of Hawking's original calculation suggests it is lost forever, which would mean our most fundamental understanding of physics is fundamentally wrong. To resolve this paradox, physicists have been forced to propose extraordinary ideas about the black hole's final act. One compelling theory is that black holes do not vanish entirely but instead leave behind a stable relic. Imagine the evaporation process slowing to a crawl as the black hole approaches the Planck mass, the smallest possible unit of mass in quantum gravity. At this point, it would be a particle of incredible density, a billion times heavier than a proton but smaller than an atom. This relic would be a permanent fossil, a tiny time capsule containing all the information the black hole ever absorbed, encoded in its quantum state. It would be immune to further decay, a stable remnant of a once mighty cosmic giant, drifting through the cold, dark future universe for all eternity. This elegant solution preserves information but raises new questions about the nature of these bizarre particles and what laws would govern their behavior. An even more radical proposal is that the evaporation process itself is not the end but a transition. Some theories within loop quantum gravity suggest that the immense gravitational collapse could reach a point of maximum density and then rebound, much like a ball compressed to its limit. In this scenario, the black hole wouldn't evaporate but would undergo a quantum bounce, transforming into a white hole, a region of space-time that violently expels all the matter and energy it once consumed. From the outside, this would look like the delayed detonation of the original black hole, spewing out its contents billions of years after they fell in. This would be the ultimate cosmic recycling program, where black holes are not endpoints but temporary repositories, eventually returning their captured information to the universe in a grand, fiery conclusion. The implications of this metamorphosis for the far future of the cosmos are hauntingly beautiful and desolate. In a future trillions upon trillions of years from now, long after the last stars have burned out and the galaxies have drifted apart into an endless, expanding void, the black holes will be the last significant structures. They will silently dominate the darkness, their slow evaporation the only major events left in the universe. And when the very last black hole finally winks out of existence in that final burst of light, the universe will enter its final, quiet state. A thin, cold gas of photons and subatomic particles, diluted by expansion to near nothingness, all structure and complexity forever lost. This is the heat death, the ultimate triumph of entropy. Yet, if the stable relic theory is true, the universe will not be entirely empty. It will be filled with these invisible quantum fossils, each one a silent monument to a galaxy that once was, holding within it the complete history of a lost cosmic era, a library of information with no one left to read it. The metamorphosis of black holes is not just their own story. It is the story of the universe's final chapter, written in the slow fade of gravitational giants. This mind-bending concept brings us to a theory that might just be the most revolutionary idea in all of physics, one that suggests our perception of reality itself is a magnificent illusion. We are now venturing into the holographic principle, a profound concept proposing that our seemingly solid, three-dimensional universe might actually be a projection, a cosmic mirage emanating from information encoded on a distant, two-dimensional surface. And the most compelling evidence for this extraordinary idea comes from the most information-dense objects we know, black holes. The story of the holographic principle begins not with the vastness of space, but with the thermodynamics of these dark giants. Physicist Jacob Bekenstein made a startling discovery when he realized that a black hole's entropy, a measure of its hidden information or internal disorder, is not proportional to its volume as one might expect, but to the surface area of its event horizon. This was bizarre. In our everyday world, the information capacity of any object, like a hard drive, depends on its three-dimensional volume. But Bekenstein's calculation, later refined by Stephen Hawking, showed that the maximum amount of information a region of space can contain is defined by the area of its boundary, not the space within it. It's as if the entire three-dimensional interior of a black hole is described by a theory that lives on its two-dimensional surface. This was the first crucial hint that the universe might operate like a hologram. Think of an ordinary security hologram on your credit card. It's a flat, two-dimensional piece of plastic, but when you tilt it, it creates the stunning illusion of a three-dimensional image floating in space. The information for the entire 3D structure is contained on the 2D surface. The holographic principle applies this same concept to the entire cosmos. It suggests that all the information needed to describe every star, every planet, every person, and every event within our three-dimensional universe is actually stored on a vast, distant two-dimensional boundary that surrounds us. What we experience as depth, volume, and solidity is a projection, a decoding of that information into the rich tapestry of reality we perceive. We are, in a very real sense, living inside a hologram. Black holes are the ultimate test case for this principle because they represent the absolute limit of information storage. The Bekenstein-Hawking formula gives us the exact number of bits of information a black hole can hold based on its surface area. String theory has successfully derived this formula by counting the number of quantum states on a black hole's surface, providing a stunningly precise mathematical confirmation. This means the mind-boggling complexity of a black hole's interior, everything that has ever fallen in, is perfectly and completely described by quantum processes taking place on its event horizon. The black hole doesn't have a secret interior life. Its entire existence is painted onto its surface. This radical perspective offers an elegant and beautiful solution to the infamous black hole information paradox. If a black hole is truly holographic, then information is never actually lost inside it. When an object falls in, its information isn't crushed at a singularity. Instead, it is scrambled and encoded onto the event horizon itself, imprinted onto the fabric of space-time in tiny units of area known as Planck areas. Then, as the black hole evaporates via Hawking radiation, this encoded information is slowly and carefully emitted back into the universe, imprinted onto the radiation itself. The information was never truly gone. It was just translated into a different holographic language. The paradox vanishes because the fundamental unit of reality isn't matter or energy, but information. The implications of this principle stretch far beyond black holes, potentially offering a unified framework for the two great pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics is a theory that describes the behavior of particles and fields in a fixed, flat background space. General relativity describes gravity as the curvature of that dynamic, flexible spacetime itself. For decades, these two theories have been utterly incompatible. The holographic principle bridges this chasm by suggesting that gravity in a three-dimensional volume like our universe is actually emergent. It is not a fundamental force, but a consequence of the quantum interactions taking place on the two-dimensional boundary. Gravity and the very dimension of space itself are holographic projections, a cosmic illusion that arises from a deeper, simpler quantum reality that has no gravity at all. This means that the search for a theory of quantum gravity might be leading us in the wrong direction by trying to quantize gravity in three dimensions. Instead, the true theory might be a quantum theory without gravity that lives on the two-dimensional boundary of the universe. The gravity we feel and the three-dimensional world we see would then be a shadow, a projection of that lower-dimensional quantum reality. We are like the prisoners in Plato's cave, mistaking the shadows on the wall for the true forms. The holographic principle suggests that if we could ever decode the information on the cosmic boundary, we would understand that everything we see and experience is a magnificent, dynamic hologram, with black holes serving as the universe's clearest and most profound clue to our own illusory existence. This brings us to a theory so all-encompassing that it positions black holes not merely as inhabitants of the cosmos, but as its fundamental architects. The black hole universe theory proposes that these gravitational giants are the primary engines of cosmic evolution, intricately woven into the fabric of existence from the very largest scales down to the birth of individual stars. This is no longer just about what falls into black holes, but about how they actively shape the universe around them, governing the growth of galaxies and potentially dictating the fate of all cosmic structures. The evidence for this profound connection begins with a startling correlation that astronomers have observed: the remarkable relationship between the mass of a galaxy's central supermassive black hole and the properties of the galaxy itself, particularly the velocity dispersion of the stars in its central bulge. This means that the larger the black hole, the faster the stars are zipping around the galactic center. This tight correlation is astonishing because the black hole's mass is minuscule compared to the entire galaxy, often less than 0.1% of the galaxy's total mass. How can such a tiny object confined to the very center possibly know about or influence the motion of stars tens of thousands of light years away? This cosmic synchronization suggests a deep and fundamental link, a shared history of growth between the black hole and its host galaxy that points toward a co-evolution, a dance of development spanning billions of years. The mechanism for this influence is as powerful as it is destructive. This process is known as feedback. When a supermassive black hole is actively feeding, consuming vast amounts of gas and dust, it doesn't do so quietly. The immense gravitational energy released powers incredibly luminous objects known as quasars and active galactic nuclei, and it can also drive colossal outflows of material. These are not gentle breezes, they are hyper-energetic winds and jets of particles that scream out from the black hole's poles at nearly the speed of light, slamming into the surrounding galaxy. This has a dual, paradoxical effect. In the short term, these outflows can be so energetic that they literally blow the galaxy's future fuel, the cold gas needed to form new stars, clear out into intergalactic space. This effectively shuts down star formation in a dramatic event known as quenching, putting the galaxy on a path to becoming a red and dead elliptical galaxy. Yet, in a fascinating twist, these same violent outflows can also have a constructive effect. By shock compressing distant clouds of gas, they can actually trigger new waves of star formation in other parts of the galaxy. A black hole, therefore, acts as a cosmic regulator, a gravitational thermostat that can both heat and cool, destroy and create, ultimately determining the life cycle of its entire host galaxy. This theory elevates black holes from being passive inhabitants to active governors of the cosmic landscape. Their gravitational influence doesn't end at the edge of the visible galaxy. They reside at the heart of an immense halo of dark matter, and their formation and growth are thought to be the initial seeds around which this entire structure coalesced. In the early universe, a massive primordial black hole, or one of the first stellar remnants, could have provided the necessary gravitational kernel to attract dark matter, which pull in the normal matter that eventually formed the first stars and the proto-galaxy. This makes them the anchors of the cosmic web, the gravitational nails upon which the entire visible universe is hung. Their explosive deaths through mergers and quasar activity didn't just shape their individual homes, they enriched the entire intergalactic medium with heavy elements forged in their accretion disks and spewed out by their jets, seeding future generations of stars and planets with the chemistry necessary for life. The supermassive black hole is not a silent monarch but an active participant in the life of its domain. Its growth and activity inextricably linked to the growth and activity of the galaxy it calls home, forever binding the destiny of the largest structures in the universe to the behavior of the most extreme. From the gateway theory that reimagines black holes as cosmic birthing chambers for new universes, to the holographic principle suggesting our entire reality might be a projection from a two-dimensional boundary, each idea we've explored fundamentally challenges our perception of existence. We've grappled with the paradoxical nature of information, questioning whether it's lost forever in a singularity, preserved on a quantum hairy surface, or encoded across a holographic film. We've considered whether the dark matter shaping our galaxies could be a swarm of ancient primordial black holes, and whether the dark energy accelerating the cosmos might somehow be generated within their enigmatic cores. The possibility that black holes themselves could be conscious entities, or that they are the universe's ultimate computational devices, pushes the very boundaries of what we consider possible, blurring the line between astrophysics and philosophy. These are not just abstract speculations, they are serious hypotheses born from the deepest equations of general relativity and quantum mechanics, representing the bleeding edge of human curiosity. They reveal a universe far stranger and more inventive than we could have ever imagined, where the most destructive objects in existence might also be the greatest creators, and where the keys to understanding reality itself are hidden behind the event horizons of these gravitational Goliaths. The journey to unravel these mysteries is far from over. Every new observation from gravitational wave detectors like LIGO and Virgo, every fresh data set from telescopes peering at the hearts of distant galaxies, brings us closer to answers that could rewrite our textbooks and reshape our cosmic identity. This ongoing quest is a testament to our insatiable desire to understand our place in the cosmos. It's a journey that requires not just advanced technology, but immense creativity and the courage to follow the math wherever it leads, even when it points to conclusions that seem ripped from science fiction. Now, we want to hear from you. Which of these 25 theories resonates most deeply with your view of the universe? Do you find the elegance of the holographic principle compelling, or does the cosmic evolution of black hole universes capture your imagination? Share your thoughts in the comments below. We're fascinated to continue this conversation with you. If you've enjoyed this voyage to the edge of physics and reality, be sure to subscribe and hit the notification bell, because we have countless more mysteries of space, time, and existence waiting to be explored together.